today we are talking about equilibrium and Le Chatelier's principle, and we're going to start with this equation here with 2 moles of sulfur dioxide reacting with oxygen to make 2 moles of sulfur trioxide, and this is an equilibrium reaction. That it is reversible, so we'll go back and forth. And the forward reaction gives off 99.2 kilojoules per mole of heat, which makes it an exothermic reaction. Okay, so with this, let's start with our definition of equilibrium. And equilibrium happens when the forward rate of reaction is equal to the reverse rate of reaction. Okay, so I'm going to give you guys 2 scenarios here. One scenario, and it's going to be shorthand, it's not going to be the actual equation, but if we are turning SO2 into SO3, and then we have the reverse reaction, which is turning the SO3 into SO2 again. We have situation A and situation B. If if situation A, we are creating SO3 at 0.5 moles per second, and the other one, the SO3, is creating 0.7 moles per second of SO2, is this at equilibrium? Why not? No, they are reversible. These are the reverse reactions, and they're occurring at the same time. Okay, this is the forward reaction. This is the reverse reaction. Okay, but are the rates equal? No. The rates are not equal. Okay, what would be the result of this? What would you see happening? Okay, you should start seeing an accumulation of which compound? Which one is making more every second? This bottom one is making more, right? So we would see an accumulation in SO2, right? We would start, there'd be more and more SO2 building up, and the concentration of SO2 would increase. And that's not what happens according to what we've studied so far. That equilibrium happens when the concentrations of all the products and reactants are stable. When they stop changing, that means that our forward reaction rate has equaled our backwards reaction rate. Okay, so what would be examples for values to put in here for B? What could we just 0.4 and 0.8? If I put 0.4, what goes here? 0.4, right? Because the rates have to be equal to each other. The number of moles per second that are produced, 0.4 moles per second. Situation B here is then an equilibrium situation because the forward rate is equal to the reverse rate. Okay, so what factors? We've talked about this before. There are certain factors that affect reaction rate. Okay, there are certain factors that affect the reaction rate. Do you guys remember what they are? Temperature is one. Concentration. Pressure, good. And a catalyst. Okay, these are the big 4. There are a couple others. The particle size will cause something to react faster. But that doesn't really have an effect on equilibrium. And there was another one. And stirring it also won't really have an effect on the equilibrium because you'd be stirring both things equally if you were to agitate your solution. So these are the big 4 that we're going to talk about. Okay, so these factors also affect equilibrium. Okay, and we're going to have a definition here. If if one of these factors affects one direction more than the other, okay. Oh no, Zane's leaving the band. Okay. Okay. If get one direction, get it? See. Okay. If these factors affect one direction more than the other, it is called a stressor. It is something that is stressing the equilibrium. Okay, which brings us to Le Chatelier. Okay, Le Chatelier, Chateliere. No, IER apostrophe S. Le Chatelier with an accent circonflexe sur la A. Okay. It's a name in French, Joseph. All right. There isn't really a translation. Actually, that's not true. It's the Castler. It's the Castler. It would be similar to a no, it would be like someone that runs a castle as if it was a hotel. Okay, Le Chatelier's principle is this. Okay, that is Le Chatelier's principle. If there is a stress upon a system at equilibrium, the system will shift in a direction that alleviates the stress. All right? Le Chatelier is a jerk. If you are trying to do something to your chemical system, Le Chatelier will do what it can to undo what you have done. We're going to rewrite our equation here. We have our 2 SO2 gas plus O2 gas makes 2 SO3 gas plus 99.2 kilojoules per mole. Now, I want you to think about this. This is an exothermic reaction. We've already determined this. So this is exo. Joseph?
I thought the 99.2 kilojoules was negative.
It is, but notice I didn't write delta H here.
Oh, okay.
Okay, so here's the idea. This is an exothermic reaction. We've determined this is exothermic reaction. What would it seem like if you're viewing this reaction? Would you be able to feel the exothermic reaction? You could tell that it was getting warmer, right? So if we were to talk about the heat, how would you describe the reaction in terms of what it's doing with the heat? Would it be using heat? Not really. It would be doing what? Releasing heat, or what else could you call it? It could be releasing energy, releasing heat. There's a P word I'm looking for. Okay. Well, this is a product here, right? And so reactants react to produce products, right? Well, would it make sense that an exothermic reaction would produce heat? Yeah? Okay, I want you to keep that in mind, because if we think of an exothermic reaction as producing heat, then we could write that heat as a product instead of writing as delta H minus 99. Okay, all of a sudden it would be plus 99 over here on the reactant side of the equation. Yeah? This thing plus 99 with as a product is the same thing as writing negative 99 as a delta H over here on the side. You guys follow that? Yeah. Okay, you will see it both ways. You could see it like this, where delta H is written to the side. You could see it where it is actually written as a product. Okay, if it was written as a reactant, that means you would need the energy in order to go in that direction, right? Well, if you need to introduce energy to a reaction, it is what kind of reaction? It is endothermic in that case. And so if you see energy as a product, okay, then if you see energy as a reactant, then it would be an endothermic reaction. Okay, usually you see it usually you'll see the reaction as written so that the energy is a product. And so they usually write the forward reaction as the exothermic reaction. Okay. So here's what we're going to do. We're going to talk about a stress. Okay, so I'm going to give you guys a stress to the system. We're going to talk about how it shifts. Okay, in which direction it will shift. And then we're going to talk about sort of an ancillary thing, but it's like an effect of the shift. And we're going to talk about how it affects the oxygen concentration of our reaction. All right, so the first one we're going to do is we're going to decrease the temperature. Okay, if we decrease the temperature, I'll walk you guys through it. If we decrease the temperature, Le Chatelier, being the jerk that he is, wants to do what? He wants to increase the temperature, right? The way that he increases the temperature is by producing more heat. Okay, so to produce more heat in order to increase the temperature again, he is going to shift the reaction towards the side that produces the heat. Okay, so we'll start making more of this stuff over here, which means we will have a shift to the right of our reaction towards the products. If the reaction shifts to the right, what happens to our oxygen concentration? It will decrease. Okay, a lesson was what I'm teaching right now. Okay, a decrease in the concentration is what happens. Okay. Okay, so in this case, our oxygen will decrease. Okay, what if we decrease the SO2 concentration? Okay, I want you guys to give it a shot. Put it in your notes. What do you think is going to happen? here's the SO2. If we decrease this, okay. So hopefully you made your decision. If we decrease the SO2, Le Chatelier wants to increase SO2. In order to increase SO2, it's going to shift this way to make more of it. So it will shift to the left. Okay? If the equation shifts to the left, it makes more of everything over here, which would cause our oxygen to go up. Yeah? Okay. Here's the tough one. This is probably the hardest one to understand. If we increase the pressure on the system, this whole thing is happening in an enclosed container. If we increase the pressure in the container, which way are we going to shift? Ooh. Okay. Is there so Le Chatelier, the shift wants to decrease the pressure, right? Well, is there a direction of the reaction that would allow the pressure within the container to decrease? Nick.
If you move it to the left, you're making less heat, which would provide less pressure, wouldn't it?
That's a good guess, but that's not. There is an overriding factor on that because it's going to heat everything up, right? So, okay. If the volume of the container stays the same, but we've already increased the pressure of an equilibrium situation, we can't do anything more to the pressure, or we're not going to do anything more to the pressure. Okay, and Le Chatelier wants to decrease the pressure, so that's one variable. The volume of the container stays the same, and let's say it stays at a constant temperature. What else could change? We've tackled 3 of our 4 gas variables. What's our 4th gas variable? The number what?
The number of molecules.
Number of molecules. Is it possible to decrease the number of molecules in this reaction? How many molecules do we have to the left over here? Or moles. How many moles of gas do we have on the left side? 1, 2, 3, right? How many do we have over here? 2. So, if we could force the reaction to produce fewer moles of gas within the same container, would that not decrease the pressure? Yeah, do you see how that works? Okay, so if we increase the pressure, okay, the shift, what Le Chatelier is going to do is going to produce fewer moles of gas. And that would shift to the right. Okay, for fewer moles of gas, what would happen to our oxygen concentration? It would decrease because we're shifting to the right. To the right leads to a decrease in oxygen. Okay? That make sense? Okay. That's where we're stopping for today.